Welcome to the third lecture on C-star algebras titled States and the Gelfand-Naimark-Segal theorem. This is part 2 of this lecture titled States and Hilbert spaces. Let's review the first part of our lecture. We define a positive element of a C-star algebra as an element of the form x star x, and we characterize those elements as being the self-adjoint elements whose spectrum is a subset of the positive half-line. We also define the notion of a positive linear functional as being a linear map from the C-star algebra to the complex numbers which maps positive elements to positive values. We do not assume that positive linear functionals are continuous. The use of these tools is the definition of certain positive sesquilinear forms which you obtain for any positive linear functional phi by stating the pairing of A and B to be phi of A star B for any element A and B in your C-star algebra. And our purpose is really to define actual inner products from these positive sesquilinear forms on the right object. So in order to achieve that goal, we actually have a little bit of work to do. We want first to show that our positive sesquilinear forms are in fact Hermitian. We also would like to show that the Hilbert space we could construct using one of those positive sesquilinear form and doing the quotienting completing procedure actually carry an action of the original C-star algebra. And also, for all of these to be of any use, we'd like to show that there actually are actually a reasonable supply of positive linear functionals for an arbitrary unital C-star algebra. Those are the questions that we are going to answer in this lecture, which we conclude actually with the proof that any unital C-star algebra is star isomorphic to some C-star subalgebra of the C-star algebra of bounded linear operators on some Hilbert space. So I'm going to first prove that my sesquilinear forms are indeed Hermitian, and to that end I'm really going to prove that positive linear functionals over unital C-star algebras are self-adjoint, in the sense that a linear map between two C-star algebras is self-adjoint if it intertwines the adjoint operations. So to prove this, let A be a self-adjoint element of a C-star algebra and let phi be some positive linear functional. I'm going to define a function p which to any real number x associate the max of x and 0, and I'm also going to define a function m which to any real number x associates the max of minus x and 0. Now p and m are both continuous functions on the real line valued in the half line of positive numbers. And so by the functional calculus, since the spectrum of a self-adjoint element is a subset of the real line, I can define the element a plus as the image of a by p and a minus as the image of a by m. So using the star isomorphism property of the Gelfand transform, or if you prefer the star isomorphism property of the functional calculus here, I can conclude that a is equal to a plus minus a minus. That's easy to check. But on the other hand, I observe that a plus is self-adjoint because p is real valued, so it's equal to its conjugate. And the spectrum of A plus is contained in the positive half-line because the range of P is contained in the positive half-line. And therefore, we can conclude from our characterization that A plus is a positive element in our C-star algebra. Now, phi being a positive linear functional will take a positive value on A plus. The same reasoning shows that phi will also take a positive value on A minus, and therefore phi of A, which by linearity is phi of A plus minus phi of A minus, is a real number. Okay, so we have shown that positive linear functional take real values on self-adjoint elements. And then we do a fairly standard trick now. If we pick an arbitrary element of our C-star algebra, we can define its real part and its imaginary part as written here. Both are self-adjoint elements. And then we can calculate phi of A star, that's phi of the real part of A minus I times the imaginary part of A. This follows from a direct calculation, since A equals its real part plus I times its imaginary part. Then we use linearity of phi, and we observed, just by looking at it, that since we know that phi of the real part of A and phi of the imaginary part of A are both real numbers, we just proved that as a positive linear functional, phi takes real values on self-adjoint elements, that this quantity here is equal to the conjugate of phi of the real part of A plus I times phi of the imaginary part of A. which of course we recognize again using linearity as being equal to the conjugate of phi of a. So phi of a star equals the conjugate of phi of a, and we are done proving that phi as a positive linear functional is indeed self-adjoint. Now, a little corollary is that in fact, indeed, this sort of pairing we define using positive linear functional on the previous slide is not only positive and sesquilinear, it's actually also Hermitian. And the proof is this one line. If you take any two element AB in your C-star algebra, and you look at the pairing of B with A, by definition it's phi of B star A, but we've just shown that this is equal to the conjugate of phi of A star B because the adjoint of B star A is A star B. And of course you recognize that this is therefore the conjugate of the pairing of A with B. So at this point we have that these pairings defined using positive linear functionals are sesquilinear, Hermitian, and positive. So they pre-inner products. So we have reached that point where we are now starting to be interested in seeing what sort of Hilbert spaces we can construct and what relation these Hilbert spaces have with the original C-star algebra. Now, in order for us to carry out our program, we need to actually know that positive linear functionals on unital C-star algebras actually do exist. And it turns out that the answer to this question passes through answering another natural question, which is, are positive linear functionals actually continuous? To that end, I'm going to need to use the Cauchy Schwarz inequality. So remember, if you give me a positive linear functional, we saw that we can define a pre-inner product on the C-star algebra, and so we know that the Cauchy Schwarz inequality is valid for that pre-inner product. I'm just going to prove it quickly here for this special case, but the proof is exactly the same as the proof in the general case. So let's fix phi, a positive linear functional of a unital C-star algebra. We're going to prove that for any A and B in your C-star algebra, the modulus of phi of A star B is less or equal than the square root of the product of phi of A star A and phi of B star B. So let's prove this quickly. Let A and B be two elements of our C-star algebra, and let Z be a complex number. Since phi is positive, I know that phi of the product of the adjoint of ZA plus B with ZA plus B is a non-negative number. Then I can, of course, expand the argument of phi here using the usual rules inside a C-star algebra. And then I can use the fact that phi is linear. Now, what's interesting here is that you have phi of A star B and phi of AB star. And I can use the fact that phi is self-adjoint since it is a positive linear functional. So phi of AB star is the conjugate of phi of A star B. So we get a somewhat simpler expression. And we're going to simplify this expression even further. There must exist a theta, real number, such that exponential I theta times phi of A star B equals the modulus of phi of A star B. In other words, theta is any minus any of the argument of phi of A star B. And the reason why this is useful is that now if I take a real number t, and I set z to be t times exponential of I theta, and I plug that into my equation up there, I get a very simple equation. I get that t squared times phi of A star A plus 2t times the modulus of phi of A star B plus phi of B star B, that must be a positive value. But we recognize that this is, of course, saying that a particular quadratic polynomial in the variable t, which is a real variable, is always positive. So it has at most one root. And we know exactly when that happens. And, well, if you look at what the discriminant being negative tells you, it exactly leads to the Cauchy Schwarz inequality. So I'm going to use the Cauchy Schwarz inequality to prove that positive linear functionals over unital C-star algebras are indeed continuous. And in fact, their norm as elements of the dual of the C-star algebra is equal to their value at the unit. So to do that, let's fix phi, a positive linear functional, over some unital C-star algebra, and take A, a self-adjoint element of that C-star algebra. Using our knowledge about the Gelfand transform, you see that the norm of A minus A is a positive element in your C-star algebra, because it's a self-adjoint element, and its spectrum, of course, is going to be contained in the positive half-line. And thus, if you apply the positive linear functional phi to that positive element, you get a positive value. But it immediately tells you, using linearity of phi, that phi of A is less or equal than phi at the unit of the C-star algebra times the norm of A. We can apply this result to minus A and note that the absolute value of phi of A is then less or equal than phi of the unit times the norm of A, because minus A is self-adjoint, the same result as above applies. But note that phi of A is a real number because phi as a positive linear functional is self-adjoint, so phi of A is a real number. So indeed, this was an absolute value, not just a modulus. And now I want to extract from this observation on self-adjoint elements an observation about every element in the C-star algebra. That's where Cauchy Schwarz plays a role. So let's pick A, an arbitrary element of our C-star algebra. And we'd like to know something about the modulus now of phi of A. Well, the modulus of phi of A is the modulus of phi of A times the unit, because multiplied by its unit does nothing. But then you can apply Cauchy Schwarz, and that tells you that the norm of phi of A is less or equal than the square root of phi of A star A times the square root of phi of 1 star 1, which is, of course, there phi of the unit of our C-star algebra. Now, phi of A star A, we know something about that because A star A is a self-adjoint element. So we know that the square root of phi of A star A is less or equal than the square root of the norm of A star A times phi at the unit of the C-star algebra. But now, of course, we are in a C-star algebra, so the norm of A star A is exactly the square of the norm of A. So we can take that out of the square root. Norms are non-negative. And then you see we have the square root of phi of the unit multiplied by the square root of phi of the unit, which actually is phi of the unit because the unit is a positive element and phi is a positive linear functional. Therefore, we know that phi of the unit must be some sort of non-negative number. And there we have it. We have shown that for any element A in our C-star algebra, the modulus of phi of A is less or equal than the norm of A times phi of the unit. So we've certainly shown that, first of all, positive linear functionals are continuous. And second of all, the norm of the linear functional, positive linear functional phi here is less or equal than phi at the unit. But we get equality simply by plugging A equals the unit, because in that case you simply get that phi of the unit, of course, is equal to the norm of the unit, which is 1 times phi of 1. So we see that indeed we have equality. Now, amazingly, a continuous linear functional over a unital C-star algebra is positive if and only if its norm equals its value at the unit. Indeed, we've just seen that if phi is a positive linear functional, then the norm of phi equals phi at the unit. So we're interested in the converse now. Suppose we given a continuous linear functional over a C-star algebra A with a unit, such that the norm of that continuous linear functional equals its value at the unit. And let's call that linear functional phi. Let's pick A, a positive element in our C-star algebra. We want to prove that phi of A is positive. To do that, first, I want to remind you of a result from the previous lecture. If t is greater or equal than the norm of A, then because A is positive, the norm of t minus A is less or equal than t. That's a characterization of positivity we obtained in our previous lecture. I'm applying this to the special case t equals the norm of A. That gives me this little inequality here. And now I go on to perform a simple calculation. So the norm of A times phi of the unit minus phi of A. By linearity, that's of course phi of the norm of A times unit minus A. And then using continuity, this is less or equal than the norm of phi times the norm of the argument, so the norm of A minus A. And we saw just now that by characterization of positivity, the norm of A minus A is less or equal than the norm of A. So I end up with the norm of A times phi of the unit minus phi of A is less or equal than the norm of phi times the norm of A. But remember, the norm of phi, that's a key assumption here, equals to phi at the unit. So I can replace the norm of phi by phi of the unit. And now look at, as usual, the beginning and the end of this series of inequalities. If you can cancel on both sides the norm of A times phi of the unit, you're left with minus phi of A is negative. Or in other words, phi of A is positive. So here's our main existence theorem about positive linear functionals. Again, we work within a unital C-star algebra. Let A be a self-adjoint element within that C-star algebra. Then there exists a positive linear functional, phi, which maps the unit to 1 and so that the absolute value of phi of A equals the norm of A. Remember, A is self-adjoint, phi is positive linear functional, so it's self-adjoint, so phi of A is a real number. So let's prove this result. And the key observation here is that the C-star algebra generated by self-adjoint element A in the unit is abelian, so it has plenty of characters. In fact, I know that the Gelfand transform of A is an homeomorphism from this Gelfand spectrum onto the spectrum of A. So there must exist a character, omega, such that the absolute value of omega at A is the spectral radius of A. That follows from the compactness of the spectrum and the homeomorphism property I just mentioned. So since A is self-adjoint, I actually know the norm of A equals its spectral radius, so it's equal to this absolute value of omega at A. On the other hand, I also note that as a character, omega has norm 1 as a linear functional over the C-star algebra generated by A in the unit. But 1 is also the value that omega takes at the unit, so as a side observation, omega in particular is actually a positive linear functional on the C-star algebra generated by A in the unit. But we know that those exist because we were able to construct them in our previous lecture. And then, well, of course, I'm going to use the Hahn-Banach theorem. It tells me there must exist a linear functional, phi over A, whose restriction on the C-star algebra generated by A in the unit is omega, and at the same time whose norm is equal to the norm of my character omega, so the norm is 1. But then the norm of phi is 1, which is equal to omega at 1, of the unit, but omega at the unit is phi of the unit because phi and omega agree on the C-star algebra generated by A in the unit. And so you see by the characterization we have seen before that phi is indeed a positive linear functional. If you look at what it does at A, by definition, phi of A is the absolute value of omega of A, it's the spectral radius of A, and A is self-adjoint, it's a norm of A. Now I remind you from our previous lectures that a positive linear functional of norm 1 is called a state, and from the work we've done on the previous slides, we know that therefore states are positive linear functionals which takes the value 1 at the unit. So really this is a theorem about the existence of states. So let me show you that as a consequence, we can actually calculate the norm of an arbitrary element in a unital C-star algebra using only those states, those positive linear functionals of norm 1. So again, we work within a unital C-star algebra. Let A be some self-adjoint element. Then the first claim is that the norm of A is in fact the maximum of the absolute value of phi of A for phi ranging over all possible states of your C-star algebra. And as a consequence of that, if you pick an arbitrary A now, not assumed to be self-adjoint anymore, then its norm is equal to the square root of the maximum of phi of A star A, for again phi being a state, phi being some continuous linear functional over the C-star algebra that's positive and of norm 1. To understand this proof, it's very simple. I mean, first note that if you're a state, we've seen you're a positive linear functional of norm 1, so the absolute value of phi of A is less or equal than the norm of A, because the norm of phi is 1. So certainly we have the norm of A is less or equal than this maximum. But second of all, we've just seen that there is a state that actually achieves that bound. So that's why it's a maximum and not just a supremum. And then the general equality here for a general element, not necessarily self-adjoint, follows from the C-star identity. The norm of your element A is equal to the square root of the norm of A star A, and A star A is self-adjoint. You just apply the previous result. Since states are positive, phi of A star A is, by the way, positive, so I don't need the absolute value any longer. So now if you give me any non-zero positive linear functional, then by rescaling it with 1 over its value at the unit, you get a state. So the states are really the positive linear functionals that matter, and in particular you saw from the previous slide, they are sufficient to, say, recover the norm on the C-star algebra. So the state space is an important object, and it's simply the set of its positive linear functionals of norm 1. So it's a set of all of its states. What's notable and quite important is that if you have a unital C-star algebra, then its state space is a weak star compact convex subset of the dual of the C-star algebra. So I'm first going to prove the state space of a unital C-star algebra is weak star closed. So let phi sub j be some net of states which converges in the weak star topology to some phi, which is a continuous linear functional for all I know at the moment. If I take A, a positive element in my C-star algebra, then I know that for any j in my index set, phi j of A is positive because the element of my nets are all states, they're all positive linear functional. So the limit of a net of positive number being positive, phi of that element A at the limit is again a positive element. So certainly the limit in the weak star topology of a net of states must be a positive linear functional, and that is actually always true whether the C-star algebra is unital or not. However, the norm of that limit, of course, we don't know because we only have this weak star convergence. We only have an upper bound on it. But it turns out that we also know that the norm of a positive linear functional is actually its value at the unit. And then, because I have weak star convergence, I know what that is, and that's 1, since it is here the limit of a net of states. And therefore, from that, you conclude that the limit is itself a state. It is a positive linear functional of norm 1. So I've shown that the state space is closed when we're working with a unital C-star algebra. That last part, where I do invoke the unit explicitly, actually is not true for non-unital C-star algebras. But here we have this, and therefore the state space is a weak star closed subset of the closed unit ball of the dual of our C-star algebra because, well, states have norm 1. And we know that the closed unit ball of any Banach space is a weak star compact by the Banach-Alaoglu theorem. So the state space, being weak star closed in a weak star compact, is itself weak star compact. It's also convex, which is a very easy proof. So if you take any two-state phi m psi and you take a real number between 0 and 1, and you form the linear functional t times the state phi plus 1 minus t to the state psi, you want to check that you have again a state here. And while you apply it to a positive element A and it gives you a positive value, it's very easy to check. And it's also easy to calculate what t phi plus 1 minus t psi does to the unit, and it again maps it to 1. So, it's again a state. So here we have a very interesting object from a Banach space theoretic point of view. We have a weak star compact convex subset of the dual. And that weak star compact convex subset is enough to recover the norm of every element, as we saw on the previous slide. You remember that we showed that the norm of a self-adjoint element is the maximum of the absolute value of phi applied to that self-adjoint element for phi ranging over the state space. And just as actually happened in the general theory of Banach spaces, the fact we have a maximum rather than a supremum, though we were able to prove it directly using the Hahn-Banach theorem, is here somewhat quote-unquote vindicated by the fact we're taking the supremum of a quantity over a compact space, so therefore it is indeed reached. So let's now return to our original problem of studying those positive Hermitian sesquilinear form, and I'm going to focus now my attention on those forms defined using states. So in order to carry out my project, I need to study one more property, and it is how to make these sesquilinear forms into inner products by making them definite. That's what's missing. And for that purpose, I will have to quotient by the kernel of the associated quadratic form. So what the theorem here tells us is that actually the kernel of these quadratic forms are left ideals. So let's first prove the properties of this map psi defined in the theorem. So first note that psi, the unit, is indeed phi of b star b. So if psi is positive, I will get the desired norm. And to prove that psi is positive, I just take A, a positive element in my C-star algebra. By definition, it means A C star C for some C in your C-star algebra. And then if we calculate psi of A, well, that's phi of B star CB, which can be written as phi of the adjoint of CB times CB. And the adjoint of CB times CB is a positive element of your C-star algebra. Phi is a state, so it's a positive linear functional. So here we get a positive number, so psi of A is a positive number for any positive A. So psi is a positive linear functional, and its norm is indeed its value at the unit. And we are done with this. This is a little result I like. We'll see why it's useful when we prove the left ideal property of the I-phi set in this theorem. But first I'm going to prove this I-phi set, that is the kernel of my quadratic form associated with my sesquilinear form here, is indeed a subspace. I need to start with that. This is a corollary of Cauchy Schwarz. It's in fact the corollary of the Minkowski inequality, of course. So I'll just reprove it here quickly, just so that our proof is complete. So if I take any two element A and B in I sub phi, and I calculate phi of A plus B star times a plus b. So I'm trying to prove that a plus b is in I phi. So I would like that to be 0. Then, well, what I do is I expand using linearity of phi. Then I use the fact that phi being a state, it is self-adjoint. So phi of a star b equals the conjugate of phi of a b star. So I get that this expression here, that is phi of a star a plus twice the real part of phi of a star b plus phi of b star b. And then the usual trick that you are likely familiar with is to observe that twice the real part of phi of a star b is less or equal than twice the modulus of phi of a star b, and that by Cauchy Schwarz is less or equal than the twice the square root of phi of a star a times the square root of phi of b star b. And then it's a perfect square, you factor. And what you know is that since we chose a and b in I sub phi, phi of a star a is 0 and phi of b star b is 0. So this expression here is 0. And here, this is all I need because I know that a plus b star times a plus b is a positive element in my cyst algebra. Phi is a state, so phi of that positive element is a positive number, but that positive number is less or equal than 0, so it's 0. So a plus b is indeed in I sub phi. It's trivial to check that, of course, if you multiply an element of I sub phi by some scalar, then it's still in I sub phi. That's immediate since our pairing here is sesquilinear. And of course 0 is in I sub phi trivially. So we've shown that I sub phi is a subspace of our cyst algebra. Now I'm going to prove it's a left ideal, so what's left is to prove that if I take an element of my left ideal, let's call it A, and I multiply it on the left by something else, let's call it B, then I should be falling back into my left ideal. So let A be in I phi. That is, it's an element, so that phi of a star a is 0. And let B be arbitrary in my cyst algebra. And this is why I'm using this nice observation we made about the map psi at the beginning of this proof. Because if you calculate the modulus of the product, it's soon to be inner product of BA with BA, then, well, by definition, it's phi of a star BA. And you recognize that this is of the same form as the psi map here, so I can conclude using what we've done recently that this is less or equal than phi of a star a times the norm of b star b. And what do I know about the phi of a star a? Well, I know it's 0. So I can conclude that indeed BA is also an element of I sub phi, so I sub phi is a left ideal. So this is important because if you try to multiply on the right, see what happens. And because of the lack of commutativity, you'll get stuck. So it is not a right ideal in general, but it is a left ideal. Why is that good? Well, here is now the key of this whole story. I'm going to, at last, construct a Hilbert space out of all of these ingredients. So I start with some unital cyst algebra A, and I pick a state in that unital cyst algebra. Call that state phi, and as usual define this Hermitian positive sesquilinear form by setting for any A and B in your cyst algebra that the pairing of A and B is phi of A star B. So we know, as I say, it's a pre-inner product. And we have this kernel of the associated quadratic form, that's a left ideal. As a little side note, it's actually closed because it's a kernel of a continuous map, but that's not going to be used in this slide. Okay, so I'm going to check that if I take two arbitrary elements A and B in my cyst algebra, and I add to them two elements that come from this ideal, this kernel of the quadratic form, then I don't change the value of the inner product. That should be to be expected. I mean, this is the whole point here, of course, of this kernel. So the calculation is written right here. You see that if you calculate A plus C, B plus D, where A and B are arbitrary, but C and D are chosen in the ideal I phi, the left ideal I sub phi, then you use this linearity, and then the sesquilinearity, but here I just use the fact that my form is additive to get an expression like this. You recognize at first the pairing of A and B, that's cool, I don't want to touch this, but then every other pairing has at least one element that comes from I sub phi, and then by Cauchy Schwarz, well, all of these three other pairings will have to be 0. So what we can conclude from all of this calculation is that our positive Hermitian sesquilinear form actually induces an inner product on the quotient of our cyst algebra by this left ideal I sub phi. If you take two equivalence classes in that quotient, let's call them A and B, then there is, of course, a representative X and a representative Y in the C star algebra, respectively, for A and B, and I'm going to call the inner product of A and B to be the value of the squilinear form applied to X and Y. We've checked that this is already positive in Hermitian, and now it's definite on the quotient because I factored out the kernel. Now, what I'm going to do is define a Hilbert space as a completion of that quotient for that inner product and the norm it induces, and I denote that completion as L2 of our C star algebra with a state phi. Just to be very clear, the quotient here of our C star algebra by I sub phi is not a C star algebra, it's not even an algebra, because I sub phi is not an ideal, it's just a left ideal. It is, however, actually a Banach space, because this left ideal I sub phi is actually a closed subspace, and so it is a Banach space for the quotient norm from the C star norm of the C star algebra onto that quotient. But this being said, this is not the norm I'm working with. The norm that interests me here is a Hilbert norm obtained through this construction of a particular inner product. And for that, there is no reason for this quotient to be complete. It is not in general. And, well, we're going to get to complete that space into a Hilbert space, but now we have to be careful not to confuse which one norm we're working with. So let's make this very, very clear. If you take an element B in your C star algebra, it has an equivalence class in that quotient. I'm going to denote it by mu sub phi of B. And mu sub phi of B is a vector in a Hilbert space now. It has a norm in that Hilbert space. And if you calculate the norm in the Hilbert space of mu sub phi of B, then it's less or equal than the norm of B in the original C star algebra. It's not equal, it's less or equal. And as soon as our C star algebras are infinite dimensional, we have no expectations that those norms are in fact equivalent, right? So we have this nice relation, but that's it. Why we have this inequality comes from the fact we're working here with a state, so it's a nice positive linear functional of norm 1. So in particular, what is the norm, the square, in fact, of the norm of mu sub phi of B? Well, the square of that norm is equal to phi of B star B, which is less or equal than the norm of B star B, which is, as you know, equal to the square of the norm of B, since this is a C star norm. So by taking square root, we get the inequality stated here. We have now arrived to our main result, the GNS construction or Gelfand-Naimark-Segal construction. It states that if you give me a unital C star algebra and a state phi of that unital C star algebra, then there exists a unital star morphism from that C star algebra to the C star algebra of continuous linear endomorphisms of the Hilbert space L2 for your C star algebra and your state phi. So this is already very interesting, but there is actually more. So if you call this unital star morphism pi sub phi, there exists a special vector psi sub phi in this L2 Hilbert space here, such that for any A new C star algebra, phi of A, the state that you chose, evaluated at A, is calculated as a vector state, as the inner product of the special vector psi sub phi and pi sub phi of A apply to that special vector psi sub phi. So every state of a unital C star algebra is a vector state in the sense of physics. And second of all, if you look at the set of vectors you obtain by taking this special vector psi sub phi and apply to it pi sub phi of A for A ranging over all your C star algebra, then this set is actually a dense subspace of your L2 space. Let's prove this very important result. I'm going to use the same notations as on the previous slide. So here is the idea. You pick an element A of your C star algebra. You'd like to make it into an operator on that L2 space. To do that, I'm going to use a multiplication of my C star algebra. And first, I'm going to define how A acts on vectors in the quotient of the C star algebra by this ideal I phi, this left ideal I phi. To do that, observe that if you take B an element of your C star algebra and C an element of this left ideal I sub phi, then A times B plus C minus A times B is A times C, and since C is in the left ideal, so is A times C. So if you apply the canonical surjection mu sub phi to this identity, you get that mu sub phi of A times B plus C equals to mu sub phi of A times B. In other words, I can act on the vector mu sub phi of B by A by defining the following. pi sub phi of A times the vector mu sub phi of B equals to mu sub phi of A times B. This is well defined, as I've just checked that, because if I replace B by anything else that gives me the same vector, that is B plus C for C in I sub phi, I would get the same answer. So it's easy to check, first of all, that pi sub phi of A is a linear map on this quotient of the C-star algebra by I sub phi. That simply follows from the fact that mu sub phi is linear itself as a quotient map from a vector space to the quotient of a vector space by a subspace. So, all right, the first problem to address is that the quotient A by this ideal I sub phi is dense in L2, but it's not all of L2. So to define pi sub A as an operator on L2, I'm going to first calculate the norm of pi sub phi of A applied to a vector of the form mu sub phi of B. And in fact, to do that, as usual in Hilbert spaces, I'm going to calculate the square of that norm, which is the inner product of mu sub phi of AB with itself, by definition of what pi sub phi of A is. And that in turn, by definition of my inner product, is phi of B star A star AB. But we learned that since phi is a state, phi of B star A star AB is less or equal than phi of B star B times the norm in the C-star algebra of A star A. And phi of B star B, again, you recognize that's the square of the norm in the Hilbert space L2 of the vector mu sub phi of B. So you get this inequality, which tells me that, practically speaking, pi sub phi of A as an operator on the quotient of A by this ideal I sub phi, left ideal I sub phi, but for the inner product, that operator has, in fact, norm no more than the norm of A. So in particular, it's uniformly continuous. It's a continuous linear map on a norm space, so it's uniformly continuous, and thus it has a unique extension to all of L2. I'm going to still denote that extension pi of A, and that follows from the fact that the set of vectors by mu sub phi of B for B ranging over your C-star algebra is dense in L2. Okay, so now I have defined a bounded operator, continuous linear endomorphism of L2 for each A in my C-star algebra, and I denote it by pi sub phi of A. And in passing, I noticed that the norm of the operator pi sub phi of A is less or equal than the norm of A in your C-star algebra. Now I'm interested in the property of pi sub phi as a map from my C-star algebra to the C-star algebra of bounded operators on L2. Okay? So we shift of perspective a tiny bit. So for instance, let's check that this map is an algebra morphism. And first, let's check that it's multiplicative. So if you take two element A and A prime in your C-star algebra, and then I'm going to take again an element B in my C-star algebra to give myself a vector in L2, then if I calculate pi sub phi of A prime applied to the vector mu sub phi of B, by definition of this pi sub phi of A prime, a linear operator, this is mu sub phi of A prime multiplied by B. But this last multiplication, it takes place in my C-star algebra, so it's associative. So this is mu sub phi of A times something. And by definition of pi sub phi, this is pi sub phi of A applied to mu sub phi of that something. And do that one more time, and you get the identity that for any B in your C-star algebra, pi sub phi of A prime applied to mu sub phi of B is pi of sub phi of A times pi sub phi of A prime times mu sub phi of B. Again, as B ranges over your C-star algebra, the set of vectors of the form mu sub phi of B is dense in L2. Therefore, by continuity, we conclude that we've shown that pi sub phi of A prime equals pi sub phi of A times pi sub phi of A prime. So pi sub phi is a multiplicative map from my unital C-star algebra to the C-star algebra bounded operators on L2. Similarly, you could check pi sub phi is linear, and that will follow from the fact that mu sub phi again is itself linear. As an observation, we already know that actually that pi sub phi map is not only an algebra homomorphism, it's also a continuous algebra homomorphism, because you see, we already know that if you take an element A in your C-star algebra, pi sub phi of A as a bounded operators has norm less or equal than the norm of A. So we know that pi sub phi as an operator, as a linear map from the C-star algebra A to the bounded operators, the algebra of bounded operators on the Hilbert space, has norm no more than 1. But this is reached at the unit. If you calculate pi sub phi of the unit of the C-star algebra, you get the identity. Alright, so that's interesting. But of course, here we have an algebra morphism between two C-star algebras, we'd like it to be a star morphism. So let's calculate the adjoint of pi sub phi of A for an element of our C-star algebra. To be clear, A as an element of a C-star algebra has an adjoint, namely A star. On the other hand, pi sub phi of A as a bounded operator or continuous linear homeomorphism of a Hilbert space also has an adjoint in the sense of the adjoint for inner products and all that. And what I'm saying here is I would like those to be related. I would like pi sub phi to intertwine those two notions of adjoint. In other words, pi sub phi to be a star morphism. So how do I calculate the adjoint of pi sub phi of A? I give myself two vectors in L2. I'm again going to take first vectors of a special form. Namely, I'm going to take B and C element of my C-star algebra, and I'm calculating the inner product of pi sub phi of A applied to mu sub phi of B with mu sub phi of C. Okay, so first of all, what is pi sub phi of A applied to the vector mu sub phi of B? That's the vector mu sub phi of AB. That's my definition of my action. And then, what is this inner product? Well, it's phi of B star A star times C. That's my definition of my inner product. The next step is to use associativity in my C-star algebra again to move the parentheses so that I recognize that this is equal to the inner product of mu sub phi of B with mu sub phi of A star C. And what is mu sub phi of A star C? It's pi sub phi of A star applied to the vector mu sub phi of C. Now again, as I've said many times, the set of vectors of the form mu sub phi of B for B ranging over your C-star algebra is dense in L2. So we can deduce from this identity written here that pi sub phi of the adjoint of A indeed equals to the adjoint of pi sub phi of A. So we already knew pi sub phi was a unital algebra homomorphism. Now we know it's a unital star morphism. And that concludes the first part and maybe the core of this GNS construction. But there's a little more structure. So since we have a unital C-star algebra, we have a unit. And we're going to look at what happens to the vector that is obtained by applying mu sub phi to the unit. Let's call that vector psi sub phi. So, well, first of all, pick an element A in your C-star algebra and let's do a little fun calculation. Let's look at the inner product of psi sub phi with pi sub phi of A applied to psi sub phi. By definition, it's phi of the adjoint of A1 multiplied by A times 1, the unit of, where 1 here means the unit of your C-star algebra. And, you know, simplify trivially to phi of A. So you get actually phi of A as a vector state in the physics sense. And second of all, if you take an arbitrary element A in your C-star algebra and you calculate pi sub phi of A applied psi of A, well, we just did it. But one way to look at this is that it's mu sub phi of A times 1, which is mu sub phi of A. So another way to look at this is that if you look at this set of vectors of the form pi sub phi of A applied to this fixed psi sub phi, and you let A range over all your C-star algebra, you get something dense in L2. In fact, it's the subspace exactly given as a vectors mu sub phi of A for A ranging over your C-star algebra. So that's a lot of structure, and that's very nice. We now have, I would say, the main result about the relation between C-star algebras and Hilbert spaces. We're going to prove another result, which is a corollary of this, but this is how you use it very often. You have a C-star algebra, you take a state, and now it's acting on a Hilbert space. What can happen, of course, is that the star morphism need not, in general, a priori, be injective. So there might be a kernel to it, which would be an ideal. An actual ideal, it's a kernel of an algebra morphism, and it would be a closed ideal because we have a continuous map. Star morphisms are always continuous. So, you know, we could certainly lose some information in this translation here. It will be an interesting question to know when do we have states for which this construction leads to an actual injective star morphism, and such states will be called faithful states. But for the time being, what I'm going to say is, well, I can still get that every unital C-star algebra is star isomorphic to a C-star subalgebra of bounded operators on some Hilbert space using the GNS construction. All I have to do is maybe be less demanding as to what a Hilbert space is going to be. Let's prove this important result. So you give me a state phi of the C-star algebra. There is a Hilbert space L2 of phi constructed from the C-star algebra in that state phi. We saw that in the GNS construction. And what I want to do is take the Hilbert sum for phi ranging over the entire state space of this L2 of phi's. Just to remind you what that means, first you take the algebraic sum of those L2 of phi's for phi ranging over the whole state space. So there are families of vectors indexed by the states, where for a given state phi, the component at phi is an element of L2 of phi. But with the properties that only finitely many of those vectors are not zero. That's the algebraic direct sum. Then what you do is you can, for any two of such families, you can define their inner product as the sum of their component-wise inner products. Okay? And that's legitimate, again, because this is a sum of only finitely many non-zero terms. And that gives you actually an inner product of this algebraic sum, which you can use to complete the algebraic sum into a Hilbert space. That's called the Hilbert sum of all these Hilbert spaces. Now, let's take, again, say, an element on this algebraic direct sum, which is dense in age. How do I act on that with an element A in your C-star algebra? Well, diagonally, that is, pi of A applied to that that family in the algebraic sum is simply pi sub phi of A applied to the component of that family for the state phi at the coordinate quote-unquote phi, which is what I've written here. And now there are a couple of very easy things to check, so I'll let you check that. This pi of A, first of all, can be extended to the entire Hilbert space H by continuity, just as we did before. It's a linear map. You're going to check it's uniformly continuous on that dense subset made of this algebraic direct sum, and then you simply extend by uniform continuity. And then you can check again that the resulting pi map from the C-star algebra to the bounded operators on that Hilbert space H is indeed a unital star morphism from the C-star algebra. And that's very natural, very easy to do. It really follows directly from the fact that each of those pi sub phi are unital star morphisms. By the way, it gives you for free that this pi map is also continuous from the C-star algebra to the algebra of bounded operators on Hilbert space. That's for free, but you could also see that because the pi sub phi's are all, well, pi sub phi of A, say, is always of norm less or equal than the norm of A for any A, and so the upper bound here on the norm of these operators is uniform. So this is actually an equicontinuous family of linear operators. But in any case, so far so good. The really important part now that we are left to prove is that this pi is injective. Because if it is injective, as an injective star morphism, it is going to be isometric, and as an isometric map, it's going to take a complete object, namely the unital C-star algebra, to a complete object, which will also be easily checked to be a star algebra, and so it will be a C-star subalgebra of the bounded operators on the Hilbert space, and will be done. So how do we prove that pi is injective? Well, let's first take A in the kernel of pi, and prove that A must be 0, but I'm going to first work with A self-adjoint. So let's take A in the kernel of pi, that's self-adjoint. What does that mean? It means pi of A is 0, but if you look at the definition of pi of A, it means that for any state phi, pi sub phi of A must be 0. Well, that's easy enough. And then we say, okay, but among all the state of the C-star algebra A, there is a very special one, which has a property that the absolute value of phi of A equals the norm of A. But then this state phi, I can calculate it using this GNS construction, using this vector state representation. So phi of A is equal to pi sub phi of A applied to a special vector inner product with that semi-special vector. And what matters here is that pi sub phi of A is 0. So phi of A is 0. But that means the norm of A is 0, and that means that A was, to begin with, 0. Okay, so how do I extend that to arbitrary element of my C-star algebra? As usual, let's take A in the kernel of pi. Since pi is a star morphism, we can conclude the real part and the imaginary part of A are also in the kernel of pi. So first of all, the real part of A is A plus A star over 2. And if you calculate pi of A plus A star over 2, that's 1/2 of pi of A plus pi of A star, where the star is out of pi of A now because pi is a star morphism, so it's, 0. And same with the imaginary part. But then the real part and the imaginary part of A are self-adjoint, and then in the kernel of pi, I just proved that means that both of them must be 0, and therefore A, being equal to the real part of A plus I times the imaginary part of A, must also be 0. So we have indeed shown that we have a star isomorphism from any unital C-star algebra to a C-star subalgebra of bounded operators on some Hilbert space. Let's conclude this particular lecture with this very nice and important result.